guys. Okay, so our last speaker is Karen Worcester. She's a senior ES specialist at the Central Coast Water Board. She works on water quality monitoring and assessments, and she's been doing that since 1992. She's been involved in the design, development, and management of the Central Coast Ambient Monitoring Program since its inception, and other programs including the Morro Bay National Monitoring Program, the Morro Bay National Estuary Program, the Central Coast Long-Term Assessment Network, and the Central Coast Cooperative Monitoring Program for Agriculture. In the past, she has worked as a fisheries biologist for the California Department of Fish and Wildlife, and her master's degree involved habitat preferences of the now endangered lagoon-dwelling fish, the tidewater goby. And with that, I'm going to turn it over to Karen.
Who wrote that bio? Hi, everybody. Good morning.
Back, forward. That's it.
Thank you, dear. That's great. So I have a long, lengthy title here, which you can read, but you could also think of it as Further Adventures in Data Visualization. I'd like to acknowledge Dave Parody, sitting in the audience here, who is the software developer and data wrangler, who's done a lot of the work that you'll see here today. I manage the CCAMP, Central Coast Ambient Monitoring Program, which is part of the SWAMP family of monitoring programs. And we collect a lot of data. We have a lot of data. And so we needed good tools to make use of our data, visualize it, understand it, make it available to our staff, who are definitely our primary users and audience. So I'm going to talk about that a little bit, but I'm also going to talk about our most recent data dive into a new world underground. So we've actually delved into some groundwater data over the last 6 weeks or so. So this is all kind of fresh and nowhere near finished, but I'm going to show you where we're going. So it's getting to be 10 years ago or so, our region developed a vision of healthy watersheds and set out 3 goals associated with healthy aquatic habitat, clean groundwater, and proper land management. Basically saying, 80% is healthy, 20% is getting better. So our charge was really to identify where is it healthy and what are trends in places where it's not. So for last year, I spoke at the symposium, and I really focused on the aquatic habitat component of that goal, which we had been working on. And I'm going to summarize that today because you may not have all been there, but and then move on to talk about some other things. But basically what we did is we took both our measured data as well as model data to create whole watershed assessments. And we score our sites using a number of different measures, a little like what David was talking about a minute ago, to come up with a general score for health. We assign that health score to its underlying reach. That health score travels up to the next site and so forth. And then where we don't have site data, we have model data. This is all in a web environment. It's all available online. And you can drill in, so you can come in from the outer level of generic assessment and drill into a high level of detail. So I'm going to just quickly go through the web tool that we I have now set up for aquatic life. Basically, you would select aquatic life grades. It comes up with a map of the watershed, the region scored for overall health. It drills in to a list of the hydrologic units in the watershed. You can select one, Pajaro River here. And that brings up the sites and basically all of the water bodies that we have sampled in that watershed. And I'm going to select Yagas Creek here, which got a C score. And it zooms into that vicinity of the region. It comes up with the sites on that water body and their scores. We're going to go in further to a site level of detail. And it comes up with what we call the report card for that site. You can see there are a number of different, we call them sub-indices for the report card that have scored conventional analytes, biostimulation, biology, toxicity, metals, organic chemicals, and then we also have a habitat one in the works. And we also have a human use component that looks at some drinking water measures and pathogens. So if I drill into the conventional analytes sub-index, the various measures in that index pop up. And you can see, for example, that nitrate here is scoring an F, has a maximum value as high as 22 out of 59 samples. So you get a really quick way to drill in really quickly and find out what's going on at an individual site. Just another example, the same site, organic chemicals also scored poorly, and you can see here bifenthrin is the cause. Now in this case, you notice there's lots of A's, there's lots of non-detects. So when we score organic chemicals, we're looking at the worst case score as opposed to conventionals, we're taking this simple average. So we've got some tinkering with the scoring approaches going on to sort of reflect the type of parameter we're measuring. Also, something we added this year, well, it's been in place for a long time, but we hadn't gotten it working, is there's a wiki below the report card that allows staff to get in and type a report notes, but it also has an automatic text generating tool that goes in and takes some of the summary information and generates text that goes in below the report card. And I'll show you a bit more of that in a minute. There it is. That's the minute. So for each of the sub-indices, it sort of summarizes which were the, which ones scored poor, which analytes scored well, et cetera, what was the sample count, and so forth. So it just gives you a little paragraph summary. So we don't have to write that kind of thing anymore. So that's the aquatic health component of the project. So we're working now to add groundwater and land management assessments to the report card, because those are part of the goals included in our vision. Also, this is highly stimulated by the next round of our ag order renewal process. We have our irrigated lands management program is one of the most complex and challenging programs that our board is dealing with, and the way to visualize and link surface water, groundwater data with land management is just super critical in how we address that order. So that's leading us to try to move into this realm at this point. And as our starting place, we're looking in more detail at nitrate because it's our favorite analyte in our region. And I always talk about it every time I give a talk because it's really amazing how bad it is there. So these are two maps. I don't know how well you all can see these maps, but these come straight off of our website, scored for surface water sites. This is the Salinas and Pajaro valleys, two major ag areas. The map to the left of the screen is scored on what we call our aquatic life threshold, which is 1 milligram per liter, set more to protect for biostimulation and that kind of thing. But you can see that the pattern of red on the map for the human health threshold scored at 10 is almost the same, at least for the Salinas Valley. And that's because once we get into the nitrate problems, they're so bad. They very quickly go up over the drinking water standard. A little less of a problem in the Pajaro Valley. But it's a pretty serious problem in surface water. And we have that well characterized. This came out of the TMDL for the Salinas nutrient problem. The orange line is fertilizer sales since 1928, going up through about 100 years. And you can see up in the 2008 range, it was about 30,000 tons of fertilizers sold in Monterey County per year. So a lot of fertilizers being sold. And the blue line is just the straight average of all nitrate data collected in that watershed from about 1968 on, where the concentrations have gone from, somewhere around 1 or 2 up to about over 15 milligrams per liter. I'm sure you can't see the detail on this map. This is, but this is relatively new data collected from our most recent irrigated lands order, where we have required the growers to submit both data from their irrigation wells as well as their private drinking water supply wells. So if they have a house on the property that has a well, they have to submit that data as well. I don't know if you can get a sense of the red there. Those are sites that exceed the drinking water standard, and they're, ubiquitous throughout the areas where they've delivered data, all the way up the Salinas Valley, throughout the Santa Maria area. And the statistics down below, if you can read those, the mean value for private wells was 8, with a maximum of 178 milligrams per liter in private drinking water wells. So it's pretty amazing. And in fact, those numbers are higher than the ag wells, probably because they're shallower wells. So this creates a huge environmental justice issue for many of the small ag communities in our Salinas Valley in particular, I would say. You can definitely see the very small well dots on this map. This comes straight from GeoTracker, but if you can see the maximum values for some of these wells are 300, 200, 190. This is the Soledad area. So it really is a big deal. So we wanted to do our initial data evaluation. We just took a data set from the GeoTracker Gamma data set, their publicly available data set. Much of that data is assigned to a groundwater basin and subbasin, but many wells actually fall outside of the designated basins. So we needed to find a spatial context to view that data in. So we did a geospatial join between the well locations as to surface water catchments and HUC 12s. So we're trying to make this sort of surface groundwater nexus. And so we did a join between those two types of spatial scales and calculated just straight averages at this point for the groundwater subbasins, the HUCs, and the catchments. And then for our initial scoping approach, we just set up a simple range type scoring approach, with anything scoring greater than 10 as an average being our darkest red color. We did find anytime you work with a new data set, it's hard. They say things different ways, they document things different ways, and we did have some challenges working with it. And we're hoping to work more closely with the GeoTracker staff to resolve some of those. For example, it's hard for our code and our statistics to work with zeros in the data. In some cases, non-detects are represented as zeros. That kind of thing where we're hoping we can get better access to some of the underlying information to help us with that. So in deciding on a spatial scale, we started, of course, with the Bulletin 118 groundwater basins. This is a map of those basins for our region. And you can see that in some areas, the subbasins are relatively small. There's some, again, we don't have a pointer here, but there's some tiny basins along the coastline, but a lot of them are quite large. When you just average well data at that sub-basin scale, this is what our region looks like. You can see that nice red Salinas Valley area, Santa Maria area, as well as the Carrizo Plain, which is an enclosed alkali sink area. As I mentioned, the groundwater basin size is very highly variable. The map on your left is of tiny little basins along the coastal streams in the Morbay area. On the right, you can see that area up in the upper left. Below it, you see the Santa Maria Basin and the San Ynez and San Antonio basins, quite a bit larger. So when you look at, the reason we wanted to look at these surface watersheds is that, as I mentioned, a lot of wells don't fall in an actual designated basin. So how do you assess that in an aerial extent? So in this case, to the left are the actual Bulletin 118 basins. But when you take the exact same data and look at it using HUC 12s, you can see, for example, in the, does this work? Yeah, it does. This area. Compare it to this area. So that's the San Ynez, San Antonio basins. You can see how much more detail pops out because we're using smaller areas for the assessment. And in fact, there are some problems in that basin, so it's not being averaged out. So it really sort of speaks to the need perhaps for smaller areas to look at the data And what we're doing right now, I think the computer is running as we speak, is working on the NHD catchment level. And this is the state of California. I stole this pretty map from the California Integrated Assessment of Watershed Health. So you can see that these are even smaller areas. And this is actually the level that we're doing our assessment for surface water on. So it'll enable us to pull a little more detail out of that data. This is just a map of our surface water scores, our overall health scores, laid on top of the groundwater basin scores. And you can see there's a pretty good concurrence between where our, I guess it shouldn't be a surprise, but where our problem areas are in surface water as compared to groundwater. And interestingly, you know, where we have mixed scores on surface water is where we're getting sort of fair scores for groundwater. So no surprise there, but nevertheless, it's interesting to look at it. I think it will be useful for us as we move forward with our ag order renewal. So in terms of landscape stressors, again, there's this issue of scale comes up over and over again because not only, basically it's available, there's lots of data out there and it's all available at different scales. So you have to decide what scale you're going to work at and whether you can use these different sources and either roll them upward or downward into that scale you're interested in. So for example, one of our major sources of data is the California Healthy Watersheds Assessment, and that's at the catchment level. But EPA recovery potential is another data set that has a lot of information that can be applied in this context. It's at the HUC 12 scale. We have amazing richness of data in the pesticide use database, DPR's database. That's at the township section range scale, little tiny squares, square miles. And then we're collecting data on, for example, irrigation and nitrogen application practices. That's at the ranch scale, actually at the parcel scale. I just wanted to show this map of the Healthy Watersheds Assessment as one of our major data sources. So we've pulled some of our starting indices. We're just getting going on this. That we're basically, like we did with aquatic life, we'll be creating sub-indices, one to reflect agriculture, one urban, and one that's more of a sort of general stressors. So the statewide measures that we're looking at come both from recovery potential and the Healthy Watersheds Assessment. And there are things like the percent of cultivated crops in the hydrologically connected zone. So that means the area that basically could be inundated by water. You know, it's not the riparian area. It's a large, like a flood zone adjacent to the creeks. Looking at cropland on greater than 10% slope, looking at synthetic fertilizer application, and some more generalized characterizations of agriculture that might include dry land pasture or grazing land, so forth. Some regional measures we would like to add include pesticide use, probably using the DPR prioritization model as the source of that information. We have total nitrogen applied and total nitrogen residual coming out of our irrigated lands order. Acres of drip irrigation, also out of the order. So we can look at where we have improved irrigation methods. And I don't know how wetland, well, yeah, we do have wetland treatment systems like Bryn talked about associated with some of those irrigated lands. Similarly, how am I doing time? Good? Okay. Oh, okay. With urban measures, we're looking at things like just basically what percent of urban, the high intensity urban areas, where the developed areas with high impervious cover are, and what the population density is, both in the catchment and as well as in the watershed above the catchment, because that's a stressor on the landscape. In our region, we're tracking a number of different land implementation measures, like LID acreage treated, what's the volume of our stormwater retention basins, and that kind of thing. And then we're thinking of a third index that's more of a general human stress index that has to do basically with just where do we have human use, or high-intensity human use, how erodible is the soil, there's a dam storage ratio, how much of the water is in the watershed is captured behind dams, road crossing density, and actual road density, and so forth. And then those are already available data sets, as I mentioned, in the major sources. But then other local measures that we're considering in the future might have to do with water diversions, fish barriers, miles of road treatment, and so forth. So it's obviously a work in progress. So we're probably going to be working on the groundwater data in the immediate future. I think I'm done now, so I don't need to go over this list in detail. But what I really want to say is that, first of all, it's been a great tool for our staff to get a handle on what the problems are, at least for surface water. And I think that moving into these other realms where we have that ability to drill into the causes should really help identify things to focus on. And we're also, just wanted to mention, we're working with a private software developer who's really interested in using this as sort of a pilot and running it around to some of the Silicon Valley developers to try to get some funding to take this to new realms. That's it. Thank you.